So I welcome you all to this new YouTube channel, Spark Research YouTube channel. This is Dr. V. Chandra, Assistant Professor in the Department of ECE, SRM Institute of Science and Technology. So here we are going to talk about the electromagnetic theory interference course, and in this session we are going to focus on the unit 5, that is as transmission line calculator and impedance matching advanced EM theory. So this is the new YouTube channel. I have switched to this YouTube channel, a Spark, that is a Spark Research YouTube channel, because of the technical reason. So now further, today onwards, whatever the video I am going to upload, that I will upload only on this YouTube channel, that is a Spark Research YouTube channel. Let's go ahead. So here is the syllabus for this fifth unit, and in this session we are going to talk about the stub matching introduction, and we'll see the procedure for single stub matching, and further we'll discuss a problem, that is how can we solve using the Smith chart. So first thing, what is the purpose to use this impedance matching? So as you know, if impedance is not matched, that is if impedance is mismatched, that is Z not equal to ZL, in that case we cannot deliver the maximum power. So that is why maximum, in order to maximum power transfer, we must require to match the impedance, that is Z not must be equal to ZL. So suppose if in your transmission line mismatch is there, impedance mismatch is there, then how will you match it? So answer is your, we can use some quarter wave transformer. Here we are going to use the component of your transmission line, that is matching. For this technique we are adding in the series. So here you can see this is your transmission line, and this is the components that we are going to add in series along with this transmission line. So if I'm going to add, then now because of addition of this the transformer, that is a quarter wave, because of this adding, now what will happen, the impedance will be the matching, that is now we'll receive the Z not equal to ZL. So how can we receive it? So you can check here. If you remember, this is a formula to find out the Z input. Now further here, put the L is equal to lambda by 4. So L means the beta L. So beta L equal to, further it will be the pi by 2. So here formula is ZL plus J Z naught tan of beta L. This is the for the lossy case, lossless case. So here now beta L can be replaced by this pi by 2, and now replace, and since the bit 10 pi by 2, that is 1090 is very big number, means infinity, so ZL can be neglected. Similarly here Z naught can be neglected, so ZO by ZL, that is equal to Z in. So Z in will be the Z naught into Z naught by ZL. Further now you can see, now what is our objective? Objective is to achieve the Z naught equal to ZL. So now here Z naught equal to Z in into ZL. So now you can the manipulate the Z in, and you can make you can achieve this condition, that is Z naught equal to Z of L. So this is the way to match the impedance in series. There is another technique. If you do not want to add in the series, then you can add this the sorted stub in the parallel. So this is the another technique to match the impedance match. So here how can we do? So exactly the impedance, so admittance, that is the 1 by Z, it can be written as your Y in should be 1 in order to make Z in is equal to ZO. So here Z in, that is Z in by ZO, that is the normalized one. If suppose this is 1, in that case Y normalized equal to 1. So let's suppose if it is not 1, then what can it be possible? So Y may be the have 1, that is if it is 1, then definitely it will be matched, and suppose not matching, means there will be the some components plus JB. Plus JB is the the for unknown transmission line, since we are considering that this is not the impedance matched transmission line. So suppose the impedance is different, means Zn is not equal to Z naught, in that case Y will have the 1 plus JB. So JB is the only reason because of Z0 not equal to Z0. So now further, if we wanted to the remove this JB, then we have to connect the stub in parallel such that YS should be minus JB, right? So we can write Y in is equal to 1, that is the case of the impedance matching, and JB, that is actual transmission line admittance, and plus YS, that is the for this admittance sorted admittance, that is parallel one. So we are adding this parallel, that is YS. Why are we adding? Because so that YS should be the equal to minus of JB, so that minus JB plus JB will cancel out, and finally we'll receive the Y in is equal to 1. That is our target. If it is 1, simply it means that Z in is equal to ZO, means admittance is matching, impedance is matching. So this is the another technique. Now let's solve one question. So question is here: antenna with the impedance is equal to 40 plus 30 j ohm is to be matched to a lossless line, that is 100 ohm lossless line with a sorted stub. Now we have to find the required stub admittance. So how we'll find out the required stub admittance? So now if you have the Smith chart in your hand, please take it with yourself, and now let's solve it by ourselves. So target number one, since we know the Smith chart is valid only for normalized impedance. I repeat, a Smith chart is valid only for normalized impedance, and definitely it have the length of lambda by 2. So normalized impedance. So how we'll find out the normalized impedance? So here is the not normalized normal impedance, that is ZL, and here is your ZO. So first of all, make it normalized. ZL is equal to ZL by ZO. So normalized impedance is 0.4 plus 0.3 J. Now locate this point. If you will find, so here is your x is equal to 0, this is r is equal to 1, r is your real part, x is equal to 0, x is equal to 0.5, x is equal to 1, similarly like that. So here x, now what to locate? First find out z is equal to 0.4 real part. So real part is like this, is r is equal to 1, so r is equal to 0.5 here. So 0.4 is like at this point, right? Similarly x is equal to 0.3 will be also at this point. So r is equal to 0.4 is this curve. Which curve? Here, this one curve, right? This is your r is equal to 0.4 circle, and x is equal to 0.3 circle is this one. This is the semi half circle, which is x is equal to 0.3. So draw this one like this and this. The intersection point is your ZL. So this is intersection point. Now what to do? Find out the origin. First find out your location, that is ZL, that is the this point we have already got. Now origin. Where is origin? Always remember origin is at 1 comma 0. So this is your origin. Now connect your ZL point to origin, right, and extend it. And also origin to ZL, consider this as a radius and draw a circle like this. So once you will draw the circle, then this is called the S circle. And now wherever it will cut, suppose this is this point, so this is your YL, this is the admittance, that is the another that ask in your question. So further check the values here. Now here if you will check, then r is equal to this circle, this is your r circle, so r is equal to 1.6, and j circle, this one is your j circle, so this is your something like 1.2. So this is the final value, that is the stub admittance that we need, a stub corresponding to the stub admittance, right? Now once we'll get the value, this is actually the admittance for this transmission, not the stub. So how we'll get the stub? Stub means actually not the transmission, whatever the stub we are going to add for that. So how we'll find out? So further, after finding this point, now what to do? We are going to draw the one circle, that is the this one, that is S circle, and r is equal to 1. r is equal to 1 means this circle, right? Why this circle? Because the center is at 1 comma 0. So r means the real part circle having the radius of 1, right? So now since we have drawn the two circle, that is one circle is r is equal to 1, this one, and another circle is s, that is the radius is zl, this. So now the intersection point of s circle and r is equal to one circle will have the two intersection points. Suppose the intersection points are a and b. So now extend from the 0 a point and b point, right? So corresponding to the a point and b point, now find out the j values, that is your stub admittance. So j plus and lower one is minus. So plus one is, that is the u required, that is the plus jb, and minus jb, that is the for your stub. So if you will include this stub, then it will cancel out your j extra values, whatever you have the complex quantity in your admittance. So this is the extra one that you have in your transmission line, and this is the stub that you can connect in your parallel. So this will cancel out to this one. So finally the stub admittance is your plus minus j 1.04, right? So this way we can find out. Now in your question also we have to find out the length of your stub length. So how can we find? So as we have already found the point A and point B. So what is your LA? That is LA, the distance between the load and your stub. So this is your LA, that is the, here is your transmission line, and a stub is at this point. So you have to find the distance from this point to this point, right? This is the stub. So exactly how can we find? So answer is that total length is how much? Lambda by 2, always remember, and lambda by 2, and find out this angle. So how much is this angle? So from this x is equal to 0, if you'll found this angle is 62, here it is written 62. And what about this angle? This is your minus 39. Check it. If you'll check here, this is minus 39. This is in the minus. So total lambda by 2 and minus this region, that will be the full length of your LA. So LA is equal to lambda by 2 minus 62 minus 39. So you will get the final values, this one. Similarly for your stub length, that is your L of B. L of B is your this one, that is stub length. So how will you find this one? So this one, that from origin, like here x is equal to 0 to this, how much is this? This is your, see here, this is your 62 and this is your 39. So this is your total minus this one 39. You will get this one only, this is the length. So you will get the final L of B, right? Similarly, now we can also locate the point A dash and B dash. This is your A dash and B dash, and corresponding to that, like this is 88 degree and this is also 88 degree. So corresponding to that, 88 and 272, exactly you can find out the distance where you are going to include the stub. So that's all. And then finally S values, like the intersection point of your the radius, that is S radius on this x is equal to 0. So this is the 2.7. So this is the exactly the way to find out all the values. Further also you can, if you wanted to find out the your reflection coefficient, then you can find out this divided by extending this divided by this total wherever it will cut. So this is a technique to find out, to solve the Smith chart. So I hope you got. So further, we can see some more problems related to the Smith chart. So like in the next class, in the next session, if required, we'll solve. Sure. Thank you for joining the session. And this is the old version of your YouTube link. Further, now I will share the new link. So please be here in this Spark YouTube channel only for further updates about the different session. Thank you for joining the sessions.